Hey AP, in this video we're going to talk about reactions in aqueous solutions. Before we get into our reactions, let's first talk about chemical and physical changes. So a physical change, remember, is where the physical state is altered but the chemical state remains the same. So these are things like changes in a state like going from solid to liquid, so melting, evaporating, sublimation, or just dissolving, because that's changing states going from solid to aqueous. When we go through a physical change, we break intermolecular forces. So if I have something like water here, remember we have hydrogen bonding happening, which is our intermolecular force that's happening here. Okay, it's from molecule to molecule. And when I go from, let's say this is liquid water, and I want to go to gaseous water, well, that means that I'm going to break my intermolecular forces in between molecules, or I'm going to stretch them. And so they're going to get further apart, and this is not drawn to scale by any means. But I can see that my gas molecules are much further apart. So this interaction from the hydrogen to the oxygen now is much further away than it was before. So I'm breaking my intermolecular forces. Not intra, that's within the molecule, but inter, from molecule to molecule. Chemical changes is where atoms of the substance are rearranged to form new molecules. And there are 5 indicators of chemical change since we can't see atoms. Remember, it's changes in temperature, changes in color, making an odor. If we make a gas, we see bubbles. Or if we form a solid, which is called a precipitate, which you'll see abbreviated as PPT for precipitate. These are breaking intramolecular forces, so the bonds within our molecule. So I'm breaking here and here and here and here. So if I have water, right, and I have 2 water molecules, I can break all of my bonds and turn them just into atoms. I can rearrange them. And instead, now I can make, let's see, H2O2, which looks like this, and hydrogen gas, right? I have broken my bonds. I've rearranged my atoms. I still have the same number of atoms on the left and the right, but I have changed through a chemical reaction. So chemical reactions are chemical changes. If I'm just dissolving something, I just have the same thing. I am just turning it into aqueous. So I'm changing state. Thinking about things that get dissolved in water, and if they break apart into ions, we call them electrolytes. So they're solutions with ions, and those ions can conduct electricity because they have charges, and so our electrons can jump from one to the other. Ionic compounds make strong electrolytes, which makes sense because they're made up of ions. Our generic equation is if I have a metal nonmetal, which is our ionic compound, is going to break apart into the metal cation and the nonmetal anion. Also important to note that we have to write AQ for aqueous. Molecular compounds, another word for molecular is covalent. These are weak electrolytes. Although they will dissolve, they won't dissolve into ions, they'll just dissolve into smaller versions of the molecule. So each molecule will break off from the larger molecule. So things like sugar would just break off into individual molecules. The actual, it won't break apart into ions. So they make weak electrolytes. They usually don't conduct much for electricity, maybe a tiny bit, but really not at all. We can have strong electrolytes and weak electrolytes. A strong electrolyte fully dissolves in water. So an example of that is our ionic compounds. So we can see that this strontium chloride completely dissolves into strontium ions and chloride ions because we have a one-way arrow straight to the right. Weak electrolytes only partially dissolve in water. So some ions will come off into water, but we see a double arrow here. So that means that some of our compound, and this is acetic acid, some of it breaks apart into hydrogen ions and acetate ions, but some of it doesn't. Some of it stays as acetic acid. So we have a double arrow here to show that sometimes we're over here, sometimes over here. But these usually lie on the left side because not much of it goes over to being dissolved. Then we have things that are non-electrolytes, which are just things that just don't ever dissolve in water. They just completely stay by themselves. And so we show that with an arrow and say no ionization. It's just going to stay as a molecule all together. It's not going to break apart. So things like sugar would do this. They don't ionize at all. They just stay as one molecule together. You'll notice that on your green sheets, on your reference guides, you don't have solubility rules on them anymore. So we used to give you solubility rules in chemistry, and now you don't get them anymore. So your training wheels have left. The good news is there are way less solubility rules to memorize in AP chemistry than there was to use in chemistry. And that's because you have to memorize them. So for the most part, the things that are soluble are things that end with nitrate. So all nitrates are soluble. All acetates are soluble. All compounds that begin with a group 1 metal, and all compounds that begin with ammonia. Remember, soluble means that it's AQ, aqueous. Okay. We say that everything else is insoluble unless it's otherwise stated. So you might come to a question and the question says, I don't know, that you have copper 2 sulfate, right? It's something that we've used and we know it dissolves, but it's not one of our rules, right? Copper is not a group 1 metal, and sulfate is not nitrate or acetate. But maybe in the problem it says aqueous copper 2 sulfate. Well, that tells you that, hey, this is one that is soluble, just not one that you have to know is soluble. So just note that sometimes it'll tell you that it's soluble even though it's not one of our rules, and that's okay. It is nice that you don't have a million of them to memorize. So if something is soluble, it ends in nitrate, acetate. Remember, group 1 metals are these here, okay, in our first group of the periodic table. And then ammonia is the polyatomic ion NH4 with a positive 1 charge. The reason we need to know our solubility rules is so we can make predictions about what's going to happen in our reactions, and we can get a better idea of what it's going to look like inside of our beakers. So we're going to look at a double placement reaction between potassium iodide and lead 2 nitrate. Most of you have done this lab. This is the lead 2 iodide lab. We make that bright yellow precipitate. This is that reaction for context. So first we start with potassium iodide. Potassium is K in group 1, so +1. Iodide, I in group 17, -1. Swap and drop, so I have Ki. Potassium is a group 1 metal, so this must be aqueous. Then we've got lead 2, so Pb is lead. Nit 2 tells me I have a +2 charge. Nitrate, ATE, that's NO3, -1. And that's a polyatomic ion that we'll use a whole bunch. So you'll start to get that memorized. We swap and drop. So I have Pb, NO3, 2. It's a nitrate. Nitrates are soluble, so AQ. Okay. I need to predict my products. It's a double placement reaction, so my potassium and my lead swap places. So I have lead 2 iodide, and potassium kicks the lead out, so I have potassium nitrate. Okay. So lead 2 iodide, lead 2, Pb +2, iodide is I -1, right? They haven't changed. So swap and drop, Pb, I, 2. Lead is not group 1. Iodide is not an acetate or a nitrate. So it's not one of our soluble compounds, so it must be a solid. Then my last one, potassium. Potassium is K +1. Nitrate, we had before, NO3 -1. Swap and drop, they're both 1s. So K, NO3. Starts with a group 1 metal and ends with a nitrate. Definitely aqueous or soluble. We need to balance it. 1 potassium, 1 iodide, 2 iodides. So we add the 2. 1 lead, 2 nitrates, 1 nitrate. So we add 2 there, double check, 2 potassiums, we're good. All right, so that is the standard reaction that we have done thus far. Now we're going to look at, well, if things are aqueous, that really means that they're split into 2 ions. Their ions have split apart. So we can show that. So everything that's aqueous is going to split apart into its ions. Solid is going to stay together, but my other aqueous one's going to split apart. So complete ionic is showing all of the ions in solution. So we have 2 potassium ions, aqueous, plus 2 iodide ions that are aqueous, plus 1 lead plus 2 ion, aqueous, plus 2 nitrate minus 1 aqueous. So that's everything from the left side. On the right, this is a solid, so it stays together. PbI2 solid. And then finally, we've got 2 potassium ions, aqueous, and make sure you guys can see that, 2 nitrate ions that are aqueous. So I've got everybody written out as ions. I'll grab one more pen. We have things called spectator ions, and spectator ions are ions that don't actually come together to form a compound. They start off as ions and they end as ions. So we can see that we have potassium starts as potassium plus 1, and then we end with potassium still as plus 1. And then the other one, so we have iodide, well, that becomes PbI2. Lead plus 2 comes into lead to iodide. But then my nitrate ion just stays as an ion. So these are spectator ions because they are not turned into any sort of product. They're just swimming around in the solution to start, watching things happen, and swimming around when it's all done, watching things happen. So spectator ions, we can cancel out, and then we can write our net ionic equation. And net ionic means that what's net happening in our beaker. And these are the things that are doing the reacting. And we can see that we've got these guys left over, my iodide ions and lead to iodines, and I make my product of lead to iodide. So my net ionic equation is what is actually happening. So I have 2 iodide ions that are aqueous plus my lead plus 2 ion, which is aqueous, makes my lead to iodide, which is a solid. Okay, and this should be balanced as well. 2 iodide ions, 2 iodines, or iodides, 1 lead plus 2, 1 lead 2 here. Okay. Now, there's a shortcut to these. A lot of your practice, you'll write complete ionic and then net ionic, but eventually we'll get to the point where we don't have to write the complete ionic reaction. We can just write net ionics. So the other trick is when I looked at my reaction up here, I can see that this is my solid, okay? What I do is I pull out my solid and I say, this is the solid of my reaction. So I draw my arrow and this is what I'm making. And I look to see, well, what 2 ions make up my solid? I have lead, and lead was plus 2 because I can pull this back up. So I have lead plus 2 and I've got 1 of them. And the other ion is iodide, and I need 2 of them, so my 2 iodides. So I can just take out what's my solid, what 2 ions made my solid, make sure they've got their charges, they're balanced, their states of matter, and then I can write it as well. So we don't have to go through this step unless it asks us to. And that's the end of your notes for today.